Okay, grade 12s, good afternoon. I am going to get started and we're going to have the same rules of engagement like we do for each of these sessions. I'm going to ask you to participate if you wish by just simply unmuting and saying what you have to say. Ask what you want to ask. At some point, I may ask you to privately give me a response to a question like we did before. I expect today's class to be actually fairly short, because really all we're doing is we're extending what we did on Friday into 3-space. So I know that if you understood everything we did with 2-space, you should be able to extend it to 3-space. The only issue is, of course, 3-space for me, trying to depict it on a diagram is going to be a bit challenging because I'm no artist. So I did try to use GeoGebra and just stuff from the textbook rather than me trying to draw anything that would even look like 3-space to you. So that's kind of what we're going to be doing today. All right, just looking at the same kinds of things that we did in 2-space, extending it into 3-space. All right, so let's get started. First of all, you know that we're supposed to start off with these learning goals, so let's just go through them very quickly. We're adding to the basis vectors that we did on Friday, one more basis vector. So we did the I vector and the J vector, 1, 0, and the 0, 1 vector, the one that went along the x-axis and the one that went along the y-axis. And we're going to add to that now the K basis vector, which is the one that goes along the z-axis. So it will now have 3 components, and we're going to use those 3 components to be able to express any position vector in R3, which is 3-space, in terms of I, J, and K. And we're going to, of course, be talking about position vectors again, and we're going to be adding and subtracting vectors algebraically. So that's the gist of what we're doing today. So let's start off with a little bit of review, because like I said, a lot of it is based on what we already did in 2-space. So let's do a quick 2-space question to get us ready for the 3-space. And took this question from the textbook. We're given the vector A as being 5, -6, again, a 2-space vector. Vector B as being -7, 3, and vector C as being 2, 8. And we're asked to calculate the magnitude, just the magnitude of the combination of A when we -3 times the B, and it'll be -1/2 times the C. So we're scaling the B vector, we're scaling the C vector, and then we're going to do a subtraction of those 2 from vector A. That's basically what we're doing. So if you think about what we did on Friday, then it's a very similar exercise. I'm going to call this new vector the vector D for no particular reason. I use A, B, and C already, so I'm going to call the combination, these 3 vectors being combined. I'm going to be combining them by doing what we did on Friday. I'm taking the vector A x component, which is 5, so that's the first number here. And then I'm going to take my x component from the B vector and multiply that by -3. I'm scaling it. Then I'm going to take my C component and multiply that by -1/2, which is exactly what these 3 things are. So that's the x component from A, the x component from B, and the x component from C. The B has been scaled by -3, and the C has been scaled, again, all x's has been scaled by -1/2. I'm going to do the same thing with the y components. I'm taking the y component from the A, the y component from the B, but scaling it by -3, and the y component from the C, but scaling it by -1/2. That's all we're doing. And when we combine these, we're going to end up with these 2 components. So that's the 5 minus or plus 21, I guess, and then -1/2 times 2 gives us the 25. And then the -6, the -9, and the -4 gives us the -19. So this D is the resulting vector of carrying out that operation. Now, that's the actual vector, but what it asks us for is the magnitude of the vector. And if you remember what we did when we did magnitudes of vectors on Friday, we just simply used the Pythagorean theorem. So we're just going to have to do this to get the magnitude. Take the square root of the 2 components squared. So the 25 squared and the -19 squared. Again, the fact that this is -19 doesn't really matter, because the fact is that we're squaring it, so it's going to become positive anyway. So there is the length, the magnitude of the vector D. So again, all I'm doing is I'm reviewing the stuff we did on Friday, but let's take that now into 3 space. Oh, by the way, and this works out to the square root of 986, which is approximately 31.4. So that's your magnitude of vector D right there. Let me go into 3 space now. So in 3 space, we're adding in this new basis vector that we're calling the K vector. We already had I from 2 space, which was 1, 0. We have to add another component to it, which is the Z component. So it's now 1, 0, 0. The J vector is now 0, 1, along with 0, right? Because they have to have 3 components for each one. And the K vector is now 0, 0, 1. Okay? So that's the new one that we didn't have before. We didn't have a K vector before. But if you look at the space here, I took this directly from the textbook. You can see the I vector is the one that's coming out along the x-axis, sitting on the x-axis, going up to 1. The J vector, again, we had the J vector before, is the one on the y-axis. Not being scaled at all, just goes out to 1. And then the new vector now is the K vector. The new basis vector is the K vector, which is going upward on the z-axis, going up to 1. So there are your 3 basis vectors. And then what they've done is they've combined those 3 basis vectors to give us this position vector for some generic ABC vector. So you scale the K, you scale the I, you scale the J, and you can end up with a position vector could be anywhere in 3 space, right? Just depending on the values of the scalars that you apply to the I, the J, and the K. So that's really what the picture looks like, right? All right, so let's just get to a couple of definitions now. So by using the scalar multiples of the I, the J, and the K, it's possible to use the triangle law, which we've talked about before, for addition to write some OA vector, which is the sum of the AI, the BJ, and the CK. So these are the scalars being applied to the I, the B, and the I, the J, and the K. So it is possible to write any vector in 3 space as a combination of these 3 things. And when these 3 vectors, the I, J, and K, are used to express other vectors or to create any other vector, we're going to call them what we called them before, the basis vectors. So now we just have 1 extra basis vector as opposed to 2, which we had the last time. So let's start with our first question. It's asking you, all right, well, first of all, it says a vector OA connects the 0, 0, that's the origin, right? 0, 0, 0 to A, which is at 3, minus 1, 2. So this is a point. This is a point. Now this OA should have an arrow on top. So I apologize that not every time I refer to a vector, I have the arrow on top. I try to do it most times, but not all the time. Sorry about that. Write OA in 2 different ways. And by that I mean, we can do it this way. We can put it in just simple component form. And I said to you before that I like the convention. I know the textbook doesn't follow this convention, but I like the convention of distinguishing between a vector and a point. So if I'm giving you a vector, which is what OA is, going from O to A, going from the origin to this point, where the point is a coordinate and it has the round brackets on it. Then if I'm putting it in component form, I put the numbers, each of the components, inside of a square bracket. So I prefer if you did that when you were answering questions to me. So here are the components. It's 3 minus 1. It's the same thing as the point itself. You're going from 0, 0. So it means that if you wanted to think of it in terms of subtracting to get what the position vector is, then you're subtracting 0 from all of these points. So it'd be like 3 minus 0 minus 1. So it's still going to be 3 minus 1, 2. So that's why this represents the component form of vector OA. Well, I could also write it using the standard basis vectors, meaning what we did on Friday. So it's 3 times I, right? Minus 1 times J, or just simply minus J, and 2 times K. So that is the standard basis format. So there are 2 ways of representing the same thing, the vector OA just being represented in 2 different ways. And that's all that is, okay? Now, it's useful to have it in the standard basis form if you had something like this to do. We're given 3 points, right? There's a B, a C, and a D. Each of these points has components, and you can see the components on the screen. I'm asking to write a single vector to represent the sum of OB and OC, and then you take the difference or you subtract from that the OD vector. Remember, all of these can be represented as position vectors, right? Because OB is a position vector, OC is a position vector, and OD is a position vector. If I were to combine these in the form that I have here, I could use the basis vectors to do that, because I could represent each of these vectors in basis form. So using the standard basis vectors, I'm going to create a new vector that I'm calling the F vector for no particular reason. I'm just calling the F vector. The F vector is a result of these three things being combined. So the OB vector would be the 1 times I, the -2 times the j, and the -3 times the k. So I'm just translating this into basis form by using these as the scalars on the I, j, and k. Do the same thing with the C. The only thing is that there is no middle number. Well, not no middle number. The scalar on that is 0. So you can really say that the j is kind of missing, which is why I have 3i and -k here. There is no j. Or there is a j, but it's a 0j. So it's a 0 vector. And then I'm minusing the 4 minus 2, 3. So 4 minus 2, 3. So we know how we've done this before, where we had to combine these things by just simply adding our like terms. So you see the answer is there already. I'm taking this I, I'm adding on this I, which is a 3i, so that's like terms again, so 4i, and I'm minusing 4i here, so the i's actually cancel out. Then I'm taking the -2j, right? There's no j here. There is a +2j here, minus a minus, so that's a +2j. The j's are canceling each other out. So I have a -3, a -k, so that's -4k. Then there's a +3k here, but it's a minus plus, so it's a -3k. Let me put those together, I get -7k. So this is the format using the basis vectors, but what does that look like in component form? In component form, because there's no I and there's no j, or let's just say that they have really been made nil vectors or 0 vectors, it becomes 0, 0, -7, right? The j and the k, in a sense, have disappeared. This means that this thing is actually sitting on the z-axis. In fact, I have a picture to share with you now. I'm trying to give you a perspective on this. So I took this from GeoGebra, the website that I've been telling you about. These are the 3 vectors that we just finished combining. So I took the OB vector, and if you can kind of see here, I have a bigger picture of this on the next screen. The OB vector is this vector which is pointing down here. The reason that it's down here is because the z value is negative, and therefore it's going to be below the x-axis, and that's why it's dotted. The C vector is the same thing because its z value is negative, so it's below the plane, the xy plane. But the D is above the xy plane, so this is the 4 minus 2, 3 here. So I'm just trying to show you what they look like in 3 space. And what I did is I asked GeoGebra to combine it in this form. So the 0b, or the OB, the OC, and the -D. And what it did is it gave me this dotted line right here, which looks like it's lining up nicely with the z-axis, and that's because it sits on the z-axis. It's 0, 0, -7. This goes all the way down, 7 units down, exactly lined up with the z-axis. I did a bigger picture of it here just to sort of give you a little better perspective, but it's the same information, right? The B vector is down here, the C vector is over here, and the D vector is pointing up that way. Combining them all makes them become this vector, which is a dotted line heading straight down. Nothing, I think, particularly complicated about that. Now, let's talk about this question. Given that a vector has an initial point of P, and it gives you the coordinates of P, and an ending point of Q gives you the coordinates of Q, what position vector is equivalent to PQ? Again, I don't have the arrow on top. I should, but I don't. And what's the magnitude of PQ? Well, does anybody remember how we find an equivalent position vector in 2 space? I have a P vector, I have a Q vector. No, sorry, I said that wrong. A P point and a Q point. They're not vectors, they're points. So if I wanted to find a vector that runs from P to Q, bearing in mind what we did when we were looking in 2 space, can anybody remember how that works?
Is it head minus tail?
Absolutely. Thank you very much, Ishal. So we're going to take all of the Q points and subtract the P points because I'm going from initial P to a terminating Q. So here's what it looks like. I'm going to take the 5, which is the head of the vector, and minus the tail, which is the -2. So it's 5 minus -2. So that's going to be my new x component. My z component is going to be the -3 minus the 1, which is what it says right here. And then that just says that I think I meant y, sorry, the y component. And the z component is the -3 minus the 4. There it is. So what does that all come down to? It comes down to this: 7 minus 4 minus 7. You can do the arithmetic for yourself. I believe I'm right. I know I make mistakes sometimes, but I believe I'm right in doing it this way. 5 minus -2 is 7, -3 minus 1 is -4. Yeah, okay, so I'm pretty sure that's good. So that answers the question of what the PQ vector is. That's a position vector that runs from P to Q. But magnitude, we haven't talked about magnitude in 3 space yet. I know what we did in 2 space. Is it the same thing in 3 space? What do you think? You think I'm going to do the same thing to get the, I mean, it's not sort of technically the Pythagorean theorem, because Pythagorean theorem really relates to right triangle, which is a flat 2-dimensional, thing. I mean, do we do the same thing when we're doing with 3 space? Turns out that we do. So for the magnitude of the vector, for PQ, I'm going to do what we just did before, which is take the components, square them, 7 minus 4 and -7, square them all, add them together, take the square root. So the PQ vector, the vector that we just figured out, which is this vector over here, if I want to find a magnitude, I apply essentially what is the Pythagorean theorem, although you might think of the Pythagorean theorem as only applying to 2 space, it applies to 3 space as well. So if I have these components, I square them all, right? Again, the sign is not going to matter because I'm squaring it. Add them up, take the square root, there's my answer. I'm going to leave it as an exact form. The last time we did this, I gave you an approximate answer, but this time we're going to leave it as the square root of 114. Okay, now let's do a few more here. And I'll do the first ones with you, and then I'm going to give you some to try on your own. I'm given a point, well, actually 2 points. One is called G, one is called H, and they're points in 3 space. And I'm asked to determine each of the following. OG. Well, we did this before, right? If I have the point G, and I'm trying to find OG, meaning from the origin to G, then all I really have to do is just simply repeat the same points as components of the vector, right? It goes from 3, 1, -5. And I just put square brackets on it because I'm trying to show this as a vector. Same thing works for OH. So for OH, it will be -1, 0, and 4. There's no difference there. And then if I ask for GH, it's exactly what we just did a few minutes ago. The GH would simply be the H minus the G. So what does that look like? That means I'm going to take -1 and -3, which is a -4. I'm going to take the 0, I'm going to -1 from that, which is a -1. I'm going to take the -4, I'm going to subtract I'm going to subtract -5, which means adding 5, that gives me 1. So here's your GH. These are the components of the GH vector. Now my next question coming up is asking for the HG vector. Well, let me go back. Let me see if I can do that this time. If the GH vector is -4, -1, 1, what do you think the HG vector would be? Without having to do a lot of math, what do you think the HG vector would be? So all I'm doing is I'm just simply asking for the vector in the other direction. It's still 3 space, but what do you think would be the answer without me actually doing a whole bunch of math? I have the GH, I want the HG. Any thoughts on what I might do to get the HG vector? So the vector running opposite direction, right? We know what opposite direction means. It has the same magnitude, but it just simply points the other way. So if I have these components, would anybody like to guess what the going the other way might be?
Is it 4, 1, -1?
Oh, well done. All you did is you just simply scale it with a -1. -1 as a scalar. So all of the signs just simply changed. And now it's 4, 1, -1, exactly what you just said. Well done. So how about the OG? Well, the OG is just simply, sorry, not the OG, but the magnitude of OG. The magnitude of OG, we just did this, right? I'm asking for the size of the vector that goes from O to G. So all we need to do is just simply do what we did before. Take each of these things and square them, and then add them up, right? So each of the components, right? Remember, the OG vector is going to run from O to G, so it's going to have the same components, 3, 1, and minus 5. Take each of these things, square them, add them up. Here's my answer, square root of 35. The OH vector is not going to be any different. It's the same thing. I'm going to take each of the components. Now, one of the components is 0, so I just left it out. I take each of the components, the -1 and the -4, square them, add them up. And the answer would therefore be the square root of 17. All right, so I'm going to get to my last slide. Yes, we're almost at the end. I'm going to get to my last slide. And I'm going to see what you're going to do with each of these 3 questions. Now, when I ask, I know Jarud has his fancy keyboard, and I know the rest of us may not have the fancy keyboard. But if you just want to give a square root of an answer, these are all magnitudes. Just write square root of whatever, all right? So let's start off with the GH, and I'm just going to give you all the questions at once, and we'll see how we do with them. And you can just privately put in your answer to each of these 3. So there's GH, which should be pretty simple. Now the OG plus OH, I'll see what you do with that. I'm not going to give you any clues. And then the subtraction, the OG minus OH. I'm not going to give any clues to that as well, but I think I'm pretty confident that everybody should be able to do this without me giving you any prompts. So let's start off with this one. So these are the last 3 questions. After this, we're done. These are the last 3 questions. I'm going to ask you to give me the answers for each one of them. You can put G. You don't have to give me the whole question. Just put G and then put the answer. Put the answer for G. H, and then the answer for H, and then I, and then the answer for I. Once I have a couple of answers in, what I'll do is I will put my final answers in. But I'd like to hear from everybody by private messaging your answers for each of these. So there's G, H, and I. So I'm going to ask you to try each one of them. If you want to do them separately and put them in separately, that's fine. Or put them all in at once, that's fine as well. Let's see what you do with them. Go ahead, please. I'm going to put my mic on mute while I give you a chance to get that done. All right, I see some great answers coming in. I'm just going to go ahead and put the answers in for that first one. So this is G coming up. And I'm not only pleased with the answer, but I'm pleased that people, not everybody did, but most people did, actually simplified it as well. So you ended up with not just square root of 18, but 3 root 2. I will expect that on a test, you will simplify it down to its lowest terms. Okay, you have your calculators, and a lot of calculators are able to do that now. So well done, well done. All the people who put answers in got it right. So let me ask you to try to do, I'm not going to give you any assistance with it. I'm asking you to do H now. Putting my mic back on mute. And I am so impressed with what you're doing. So let me go ahead and put that answer in, which most of you got already anyway, but here it comes. So it's the square root of 86. Again, what you're doing here is you're taking the G components and adding them to the H components, right? So the 3 and the -1, the 1 and the 0, etc., etc. Taking those values, and then you're gonna, so when you add them together, those become the new X, the new Y, and the new Z, and then you're gonna square those and add them up, and yes, the square root of 86 is absolutely correct. All right, so one more. You're all stars in this class, really. Well done, well done. So here we go, folks. Turns out that the answer is square root of 18, all right? And hopefully you realize that you're subtracting components this time, but then ending up with the same thing as before. And you should expect the answer to be the same as G, by the way, because if you're subtracting these components, then you're going to end up with the same thing as going from G to H. That would hopefully make sense. So that is basically what I wanted to go through with you today, and I think you should be in good shape for the homework. And a lot of you have in fact done the quiz already, and I appreciate that. If you haven't done it yet, I'm going to suggest that you try to get that done. Anybody who gets everything right, I'll just leave it at that. But if you got anything wrong, what I'm doing is I'm just flipping it back to you. So I am looking forward to you getting that done, because that's a good review exercise for you. And of course, at some point, we're going to have a test on this as well. But so far, this is all we need to do for today. And I appreciate all of you showing up and giving me your input. Unless there are any questions, I'm going to leave it there for today. Any questions? Nobody? Sorry, go ahead.
Have a great day. Nothing else.
Oh, okay. Thanks a lot, Ishan. You take care. Bye-bye now.
Bye.